Okay, welcome everyone. Today we're going to be doing a study of enzyme kinetics by taking a look at the Michaelis-Menten equation. So for a quick review, we know that enzymes are proteins that catalyze specific reactions, and they are not consumed during that process. And they are quite crucial for most metabolic pathways like drug and food metabolism. It's important to note that enzymes can be saturated, meaning the reaction rate cannot go past a certain point that we'll denote as Vmax. Okay, so we see this sigmoidal curve, and we reach Vmax in red at a sufficiently high substrate concentration. Okay, so the basic reaction model we use is as shown here. So we have the reversible binding of the enzyme with the substrate to form the ES complex. But when they form a product, we neglect the reverse rate. So we only have the forward reaction there because it's more thermodynamically favorable to form the products. So the challenge here is that it's really difficult to measure these rate constants, K1, K minus 1, and K2. So we use a few assumptions that make it easier to model. And the first is the steady state assumption, meaning the change in the ES complex concentration over time is zero. And the second is that we are in an isolated system. So however much total enzyme we put into the system will always be there in either an unbound or bound state. So we're going to apply these assumptions to our model and then derive the Michaelis-Menten equation. All right, stay tuned. Okay, so we're interested in answering the question, at what rate is our product formed from this enzyme catalyzed reaction? So we can also call this V, or the velocity of our reaction. And we know that this is going to be equal to our rate constant K2 times the concentration of our enzyme substrate complex, which forms our product. We can also write the rate of change for this ES complex, and we know that this is going to be equal to the rate at which it is produced minus the rate at which it is consumed. And there's two different rates of consumption, so K minus 1 and the K2 here. And at this point, we can actually apply our first assumption of the steady state. So the steady state assumption is going to allow us to set the rate of consumption equal to the rate of production. And once we have that, we're going to be able to solve for the concentration of ES and plug that back into our velocity equation. So we can go through the steps here by setting these rates of reaction equal to each other. And it's going to be helpful for us to pull all of the constants over to the left side so we can group all of the K's together and we get them all on the left side. And it's going to be really helpful for us to simplify this term into one singular Michaelis constant called Km. Okay, so this simplification is really going to help us not only understand this equation, but simplify the work from here on out. So we're going to look at Km a little bit more in detail after, but for right now, we're going to keep going with the derivation. So here we have Km times the concentration of ES, which is equal to our enzyme concentration times our substrate concentration. And now at this point, we can actually use our second assumption of the isolated system. And in this case, I wrote it out so that we have the free enzyme concentration on the right side because we actually want to get rid of that term. So we're going to substitute in and put everything in terms of ES and E total. So we're going to perform that substitution here. And now we're going to be able to simplify this and solve for our enzyme substrate concentration. Now you could do this in a few steps, but for simplicity, I'm going to write it out here. So once we group all the terms and simplify, we have that our enzyme substrate concentration is our E total times our substrate concentration over Km plus our substrate concentration. Okay, perfect. So now the final part is that we just have to pull back our velocity equation, okay, and plug it in now that we've solved for the concentration of ES. So we plug it all in here, and we can actually make an interesting observation now, which is that previously we looked at the maximum rate of our enzyme production, okay, Vmax. We can see here that it's actually equal to what starts that numerator, K2 times E total, because if all of our enzyme is bound, then we're at the maximum rate of constant of production of our product, okay? So finally, we can write out our full Michaelis-Menten equation, where the velocity of our reaction is in terms of Vmax, and multiplied by our substrate concentration. And we have all of that divided by our Michaelis constant plus our substrate concentration. So this is our final equation. All right, and now we're going to take a look at how we can understand it. Okay, so let's look a little bit deeper at Km and try to build an intuitive understanding, okay? So if we have here our Michaelis-Menten equation, and we actually let the substrate concentration equal to Km, then what we'll find is we'll actually be able to cancel the Km from numerator and denominator, and our velocity is going to be 1/2 of our Vmax, okay? So what this means is that Km is the concentration of substrate that gives the half velocity of an enzyme reaction for a given enzyme concentration, okay? And one really helpful way I like to think about this is that Km is really a measure of how quickly an enzyme activates in relation to the substrate concentration. So for example, if we have a really high Km, it means that it takes a lot of substrate to activate that enzyme to get to that half velocity, right? So that enzyme, it's not going to get saturated very quickly. Okay. So now we can return to the graph that we started the video with and actually annotate it here with our Km and 1/2 Vmax point located in the middle. So the last content that we're going to look at today is the Lineweaver-Burk equation. Okay, so this is essentially a linearization of the Michaelis-Menten equation, so we'll be in the form y equals mx plus b. Okay, so it doesn't make as much sense to look at it in this form because there's so many reciprocals here. But when we look at the graph, it makes a lot more sense because as we can see, we're plotting 1 over V on the y-axis versus 1 over substrate concentration on the x-axis. Okay, so the axes are essentially inverted. And we'll notice that our slope is actually Km over Vmax. And that's really the most interesting point here because this relates the two constants that we've defined in this Michaelis-Menten equation that really relate and totally synergize all of our enzyme kinetics into these two values. Okay, and the last couple things here are that the y-intercept is actually going to be the reciprocal of our Vmax, and the x-intercept on the left-hand side of the y-axis is going to be negative of the reciprocal of our Km, our Michaelis constant. Okay, so this graph really helps us understand inhibitors. So the first case we'll look at is competitive, where we have a molecule that's binding the active site in place of the substrate, right? So if we have a higher substrate concentration, we can outcompete that inhibitor. And the effects that this has is increasing the Km, right? We need a higher substrate concentration to get to that half maximal velocity. But the Vmax will stay the same. If we have a really, really high substrate concentration, we're still going to get to the same maximum rate. And this is how it affects the graph, right? So we'll have the same intercept, but the slope is going to be steeper, okay? Now, we can also take a look at uncompetitive and non-competitive inhibitors. And I know they sound very similar, poorly named, but they are actually a little bit different. So they both don't bind the active site, right? But the uncompetitive inhibitor can only bind to the enzyme substrate complex when they're bound, whereas the non-competitive can bind either the free enzyme or the bound complex, right? So interestingly, in the uncompetitive case, when we increase the substrate concentration, that means there's more ES, right? Because more of it will be bound, and therefore there's more inhibitors that can bind to ES now. Okay, so it actually increases the inhibition. And the effects that this has is reducing both the Km and the Vmax. But for the non-competitive, basically increasing the substrate concentration won't have too much of an effect on this type of inhibition. So therefore, the Km stays the same, but the Vmax is going to decrease. And these are how the graphs change. So the uncompetitive, basically, the slope is the same because it's proportionally changed. And the non-competitive, we have the same x-axis intercept on the left side because the Km is still the same. So to wrap up, we described the velocity of an enzyme catalyzed reaction in terms of the Vmax, which is the maximum rate the reaction can achieve, the Km, which is the substrate concentration that achieves half of that rate, and lastly, the substrate concentration in the system. And we were able to linearize this equation and explore the effects of inhibitors on our enzyme kinetics. So thanks for watching. I hope you learned a lot, and we'll see you next time.